In this next section, I'm going to briefly discuss a particular type of modeling without getting into any of the details, but it just shows the power of modeling. And in fact, we will not be using this model in any of our scenarios, but it illustrates the power of modeling for understanding a particular exposure when we don't have measurement data. So when we try to model any kind of scenario, especially in the outdoors, first of all, we need several determinants of this exposure. We want to know the estimates of the emission of a particular hazardous chemical into the air. We need to have data regarding the meteorology and how the air moves through a particular terrain. We need to understand the source, meaning if the pollutant is coming out of an industrial smokestack, how high is the stack, and other stack parameters such as the diameter of this stack and the rate at which pollutants are being emitted from the stack, and so on. We need to understand the land use, meaning is it a very flat plain, or are there mountains, or is it an urban setting where there are tall buildings in the path? And we need to know the receptor locations. And in this context, we are referring to where the human beings are that are the receivers of this pollution, as it were. So they are the receptors. Where are they located with respect to this source or the smokestack? So just a few words about the scenario. So vermiculite is an ore that is mined in Montana. There was a big mining operation there, and it has been producing vermiculite for a long time. And the ore is then shipped to various locations around the country. And one of the uses of this is to heat up this ore to a high temperature, and it essentially sort of creates these popcorn-like structures. And this popcorn is the thing that you see when you go to Home Depot and buy potted plant, and in the soil you see these popcorn-like white structures. So that is vermiculite. So it's a common consumer product, and it turns out that this vermiculite has traces of a type of asbestos called tremolite. So while the ore is being mined in Montana, it is then shipped all over the country through trucks and trains and so on. And in every location where it's shipped to, they process this ore to produce the popcorn-like final product. So one of the places where it was shipped to was in Minneapolis, and this is a modeling of the exposure to asbestos to the residents of Minneapolis and St. Paul, because the ore processing facility was right in the middle of Minneapolis, right in the middle of the city. So the Minnesota Pollution Control Agency was very interested in assessing exposures to the residents in Minneapolis and engaged in this modeling exercise, and I'm presenting the results of this. So in order to do this modeling, we need to know the emission estimates, as I mentioned in the previous slide. So how much of this asbestos is being emitted into the air when the vermiculite ore is being heated up? What are the air patterns over Minneapolis to figure out how it disperses throughout the city? And it turns out that while the operation of this vermiculite processing started in 1936, there was really no air pollution control measure in the plant till 1972. And in 1972, a bag house, which is essentially a filter, was installed in 1972. And the facility closed in 1979. So the objective of this modeling exercise was to assess exposures for two time periods because they were very distinct. One is before the bag house installation, so 1936 to 1972, and post bag house installation, 1972 to 1989. This is a very rough schematic of the ore processing facility. So at the top of the slide, you can see that the ore is transported by rail car, and it arrives at the facility and the rail car unloading location. And once the ore is unloaded, it's sort of piled up in these stacks, and it goes into this cement block building. And from there, it is fed into these kilns that are essentially heating up the ore, and the emissions from this combustion process come out of the stacks that are shown here in the blue. There are three stacks. And after the popcorn has been created, they go into the brick building and thereby onto the truck loading area, and they are loaded into these large trucks, which are then sent to other locations. So there were two 50-foot stacks that were used in conjunction with the furnaces where the ore was heated up. In many modeling situations, we will really not have all the information that we need. So ideally, in this scenario, we would have liked to know the emissions for every year from 1936 to 1989, but actually we don't. We would have liked to have the weather conditions for every year or possibly even every day from 1936 till 1989, and we don't. And so we do the best with what we have. And it turns out that of the entire time period, 1936 to 89, only 2 years, 1977 and 1985, reported the emissions from the stacks. We also have some information about how efficient reducing the amount of particles being emitted into the city air. There are also fugitive sources, and US EPA publishes emission factors, and these are essentially the mass of particles being emitted into the air per kilogram of ore being processed. And we also know the production rates. So, in fact, the only thing that we have annual rates for or annual information for are the production rates, because it's a commercial facility and we know exactly how much of the ore was produced every year. So the US EPA has published emission factors for the standard tasks involved in this workplace. So when we have a rail car unloading of the raw material, so per ton or per pound of raw material unloaded, how much of it becomes airborne? Same thing for when you load up a rail car or a truck, how much dust is being airborne per kilogram or per ton of finished product being loaded onto the truck. And likewise, if we have piles of either the raw material when it first came or the waste piles after the final product has been made, how much of that gets airborne because of wind erosion and other types of handling? The model we used in this instance is, again, a standard US Environmental Protection Agency model called the ISC Prime model for industrial sources, and it is described in the US EPA guideline on air quality modeling. It is essentially a Gaussian plume dispersion model that considers the effect of building wake, the wind velocity and direction, the terrain elevations, and meteorological data. The receptors for the model are located every 50 meters from the source, which is the stack, for up to 1.5 kilometers, and at every 10 degrees of the compass. In addition, receptors corresponding to all street addresses located within 500 meters of the facility. So we are assuming that that's where the people are going to be that will be affected by these emissions. So they are all the people essentially within 1.5 kilometers of this plant and at the street addresses within 500 meters of the facility. So I'm not going to describe the model at all, because this example is just to show the power of using such models. So the first slide here, it shows the dispersion of asbestos fibers as modeled for the time period 1936 to 1972. And you can see these isoplets, which are the circles of constant concentration. So you see a circle right in the middle corresponding to 0.01 fibers per cc. And then we go to 0.005 and 0.001 and extending all the way outward into the city. So there are a couple of assumptions built into this model reconstruction. The first one, which is obvious and a little bit troubling, is that for each year 1936 to 72, that's 36 years, we are assuming that this is the same. So this doesn't change from one year to the other. And this is a function of how much information or how much lack of information we have. So we have only production rates for every year, but we don't have meteorological data for every year. We don't have stack emissions data for every year. And so we have sort of an average that we have assumed for this entire time period. We are assuming that each year for all the days we have the same meteorological conditions. So the weather doesn't change and the wind direction doesn't change from one day to the other or from one year to the other. So there are a lot of very simplifying assumptions built into it. And we may debate about each one of these assumptions and how realistic or unrealistic they are. But at the end of the day, this produces a result, a map of asbestos concentrations in the city that seems reasonable. And because the underlying model has been used in a variety of similar situations, and the underlying science or the physics and chemistry of the model have been vetted. And so there is some amount of validity to the results produced by this model. Although, like I said, there are certain limitations to this as well. So when we interpret this, we need to understand the assumptions that are built into it. So we need to always understand the model assumptions and how we may want to interpret the strengths and weaknesses of the result. So this is the second part of the results. So this is for 1972 to 1989. And as you can see, the concentrations are much lower. And this makes sense because this is after the installation of the baghouse. So it has now reduced the emissions of the asbestos fibers through the stack and almost by 3 orders of magnitude. So this example just shows you the power and the limitation of using models and the care we need to have when we are using a model and understanding its limitations.